Imagine yourself standing in a laboratory at the precise moment twilight deepens into complete darkness. The air around you is utterly still, untouched by even the gentlest breeze. You notice the cool hum of precision instruments surrounding you, the faint metallic scent of cleaned steel, and the particular quality of silence that exists only in spaces designed to measure the infinitesimal. Your fingertips rest near a microscope, trembling almost imperceptibly with anticipation. Though you cannot see it with your naked eye, between two metal plates mere micrometers apart, something profound is occurring, something that should not be possible yet is. You cannot measure it with instruments alone. You must quiet your mind, as this laboratory has quieted itself, becoming patient like the darkness itself, waiting for truth to reveal itself in silence. Let yourself settle into this moment, into the gentle hum of discovery, asking nothing of yourself but the simple act of attention and presence. In the beginning, there was a question that seemed almost philosophical in nature, yet it dwelled at the very heart of physics itself. What is nothing? This question, seemingly simple in its formulation, contains within it layers of complexity that have occupied some of the greatest minds in human history. For centuries, our intuitions about emptiness suggested that the absence of something was precisely that, an absence, a void. A blank canvas upon which other things might be painted, but in itself entirely inert, entirely passive, entirely without substance or property. And yet, as the 20th century unfolded, and as our understanding of the microscopic world deepened through the lens of quantum mechanics, a most remarkable and unsettling possibility began to emerge. The void, it seemed, was not truly void at all. The emptiness between atoms was not empty. The space between stars was not empty. The very concept of empty space revealed itself to be a profound contradiction in terms. This space that appeared so placid and neutral was, in reality, seething with activity, a kind of cosmic restlessness that persisted even when all else had been removed. The implications of this realization were both beautiful and deeply troubling to contemplate. If nothing was not truly nothing, then what was the fundamental nature of reality itself? What lay beneath the surface of our sensory experience? These were questions that would draw theoretical physicists deeper into their work, searching for mathematical frameworks that could capture the strange behavior they were witnessing. The answer, when it finally began to take shape, would involve concepts so subtle and so counterintuitive that they remain difficult to grasp even today, even for those trained in the language of modern physics. To understand what happens in the emptiness between metal plates, we must first drift back through time to the foundations upon which all of modern quantum theory rests. In the early part of the 20th century, physicists discovered something that fundamentally altered our conception of matter and energy. They found that reality, at its smallest scales, did not behave as a collection of discrete particles moving through passive space. Instead, they discovered that the universe was permeated throughout its entire expanse by fields, invisible, immaterial, yet utterly real in their effects. Think of these quantum fields as an infinite ocean that fills all of space, interpenetrating everything we see and touch. Just as waves ripple across the surface of water, disturbances in these quantum fields manifest to us as the particles we observe: electrons, photons, quarks, and countless others. Picture, if you will, that ocean as the foundation of all existence. Beneath the visible world, this vast field undulates, resonates, holds within itself all the patterns that give rise to matter and light. But here lies the profound mystery. These fields do not simply rest in stillness. They are in a state of perpetual, restless motion at the most fundamental level of reality. This motion is not driven by any external force or any collision. Rather, it is built into the very nature of existence itself, emerging from the uncertainty principle discovered by Werner Heisenberg. This principle tells us that certain pairs of quantities, such as position and momentum, or energy and time, cannot both be known with perfect precision simultaneously. And so the fields must fluctuate, they must dance. Continuously throughout all of space, pairs of particles emerge briefly from the quantum vacuum, exist for the most infinitesimal fraction of a second, and then annihilate one another, disappearing back into the void from which they came. These fluctuations are not imaginary or merely theoretical. They have real effects. They leave traces. They shape the behavior of the universe in ways that extend far beyond the scales at which they occur. The vacuum itself possesses energy, an energy that was predicted but whose true nature remained deeply mysterious. Imagine stepping back in time, to the year 1948, a time when Europe was still finding its way forward, and when the scientific community was beginning to settle into a new era of exploration and discovery. In a laboratory at Philips Research in Eindhoven, Netherlands, a physicist named Hendrik Casimir was contemplating a problem that seemed abstract and perhaps even trivial to many observers. He was thinking about the interaction between the quantum vacuum and electromagnetic radiation. Specifically, he was wondering what might happen when one placed two uncharged metal plates very close to one another in empty space. Casimir possessed one of those minds that delighted in following abstract problems to their logical conclusion, regardless of how seemingly impractical such inquiry might appear. In his meditation on this scenario, he began to imagine the consequences of the quantum vacuum fluctuations we have just described. If the fields were indeed constantly dancing throughout space, then surely these fluctuations existed between the metal plates just as they existed everywhere else. But here was where Casimir's insight became truly remarkable, almost elegantly simple in its power. The metal plates themselves, Casimir reasoned, would not permit all electromagnetic fluctuations to exist between them. The presence of conducting metal would constrain which wavelengths of electromagnetic radiation could fit in that narrow space. The longer wavelengths, those that needed more room to oscillate, would be suppressed, unable to fit between the plates when they were very close together. However, outside the plates, in the vast surrounding space, all wavelengths would be free to fluctuate without restriction. This created an asymmetry, a subtle imbalance in the very fabric of the vacuum. Outside the plates, the full spectrum of vacuum fluctuations would press against everything, exerting pressure in all directions. Inside the plates, only those fluctuations with shorter wavelengths could exist. This meant that the region inside the plates experienced less energetic activity than the region outside. And if there was less activity inside than outside, then there must be a net force, a pressure from the vacuum itself, pushing the plates inward, pulling them together with an attractive force. This force, emerging from the quantum vacuum, from the fluctuations of empty space, would draw the two plates toward one another not by gravity, not by electromagnetism, but by the pressure of the quantum void itself. Casimir had predicted a phenomenon that seemed to defy all conventional expectation. Nature, it appeared, possessed a subtle elegance that few could have imagined. To truly appreciate the elegance of Casimir's prediction, we must allow our minds to settle into the mathematical abstractions from which it emerged. This is not to say we must understand every symbol. Rather, we must become comfortable with the idea that reality can be described and predicted through mathematical relationships, even when those relationships describe phenomena that seem almost impossible to visualize. The Casimir effect arises from calculations involving infinite sums and the delicate mathematics of quantum fluctuations. When physicists calculated the energy density of the quantum vacuum, they found themselves confronted with quantities that appeared infinite. These infinities did not represent a failure, but rather pointed to something deeper about the nature of theoretical description itself. Through a refined process called renormalization, physicists learned to handle these infinities in ways that were physically meaningful, allowing them to extract finite, measurable predictions from their theories. The calculation involves something called zero-point energy, the energy that remains in a quantum system even when it is at its absolute lowest possible state. In the old classical physics, the lowest possible energy would be precisely zero. But in quantum mechanics, the uncertainty principle forbids such stillness. There is always residual motion, always these quantum fluctuations persisting at the heart of existence, like a subtle vibration in the deepest silence. When Casimir performed his calculation, he considered the electromagnetic field confined between two perfectly conducting metal plates, separated by a distance we might call d. The mathematical machinery revealed something elegant. The energy difference between the inside and outside of the plates followed a precise relationship. As the distance between the plates became smaller, the effect became dramatically, exponentially stronger, a profound intensification of something already invisible. At the distances where the effect becomes measurable, the force would be subtle indeed, yet real, detectable by sensitive instruments. This relationship provided a clear signature that could be tested experimentally, a mathematical prediction that could be checked against the physical world. The decades that followed Casimir's 1948 prediction were characterized by a peculiar kind of scientific tension. The prediction was elegant, mathematically rigorous, and derived from principles that were well established and widely accepted. And yet, it seemed to describe something so delicate, so dependent on the properties of empty space itself, that many physicists were reluctant to fully embrace it. How could one be certain that such a subtle effect could be observed experimentally? Picture the laboratories of the 1950s and 1960s. Scientists bent over their equipment late into the evening, attempting to measure forces so small that they were almost imperceptible. These experiments were profoundly difficult, requiring extremely precise measurements, surfaces cleaned with meticulous care, and carefully controlled environmental conditions. The slightest vibration in the building, the gentlest fluctuation in temperature, the microscopic roughness of the metal surfaces, all of these complications interfered with the measurement. Some experiments seemed to show hints of the predicted effect, while others did not. Skepticism lingered in the minds of even the most open-minded researchers. Perfect conducting surfaces existed only in theoretical calculation, not in the real world of laboratory apparatus. But as decades passed and technology slowly advanced, the situation began to shift. Better vacuum pumps allowed for more precisely controlled conditions. Improved instruments enabled researchers to measure increasingly smaller forces with greater accuracy. A new technique called atomic force microscopy, developed in the 1980s, provided a revolutionary tool for measuring forces at the smallest scales. And theoretical work continued to refine the predictions, accounting for real-world complications. The fact that metal is not a perfect conductor at all frequencies, the subtle effects of temperature, the finite distances over which the effect extends. By the late 1980s and early 1990s, something shifted. Better experimental techniques, combined with improved theoretical understanding, began to yield consistent results. The scientific community gradually moved from skepticism toward acceptance, though a certain caution remained justified given the historical difficulties in measurement. This was not a sudden revelation, but rather a slow convergence, a careful choreography of science proceeding by incremental steps, building certainty through patient, repeated observation. Picture now the laboratories of the 1990s, where scientists were finally ready to answer the question Casimir had posed nearly 50 years before. In the University of Washington, a physicist named Stephen Lamoureux was conducting an experiment of remarkable ingenuity and delicate precision. He employed an atomic force microscope, a device capable of measuring forces at levels so subtle that they are almost beyond comprehension, to measure the attraction between a metal-coated sphere and a metal plate. Imagine the sphere positioned at varying distances from the plate, separated by distances comparable to the size of biological molecules, small enough that the quantum effects would begin to dominate. As the separation varied, Lamoureux measured the force exerted by the quantum vacuum itself, the pressure from the fluctuations of empty space that Casimir had predicted would manifest between the conducting surfaces. And the results matched Casimir's theory with extraordinary precision, better than 1% agreement between prediction and observation. After decades of skepticism, the quantum vacuum had revealed itself. But Lamoureux was not alone in this discovery. Around the same time, other experimental groups using different techniques and different configurations began to report similar findings. Researchers at the Brookhaven National Laboratory examined the Casimir effect using different arrangements of metal surfaces. Scientists in Europe and Asia pursued their own investigations, each reaching the same conclusion. The convergence of evidence was becoming undeniable. The quantum vacuum, that empty space that was not truly empty, was exerting measurable forces on the material world. And yet, even with this convincing evidence, certain questions and controversies remained. Different experimental groups reported slightly different results depending on the specifics of their geometry and their methodology. Theoretical refinements continued to be necessary to account for the complexities of real-world apparatus. The effect had been confirmed, yet its full nature and all of its implications continued to be explored and debated. This was not the end of a story, but rather a beginning, an opening into deeper understanding. As experimental evidence accumulated, physicists found themselves once again contemplating fundamental questions about the nature of reality itself. The Casimir effect confirmed that something real was happening in empty space, that quantum vacuum fluctuations were not merely abstract mathematical constructs, but had measurable physical consequences. But what exactly did this tell us about the nature of virtual particles, those ephemeral entities that appeared and disappeared in the quantum foam? The language of physics often speaks of virtual particles as if they were actual things that briefly flicker into existence and then vanish. But this language, while useful for visualization, must be understood with care. Virtual particles are not, strictly speaking, things that exist in the way we conventionally understand existence. They are rather manifestations of the quantum fields themselves, patterns of excitation that arise as a consequence of the wave-like nature of those fields and the fundamental uncertainty built into quantum mechanics. When physicists calculate the Casimir force, they are not literally summing up the effects of countless little particles appearing and disappearing. Rather, they are performing calculations involving the quantum fields and their fluctuations. The result is that energy is distributed differently inside and outside the metal plates, and this energy difference manifests as a measurable force. It is convenient to visualize this process in terms of particles, and such visualization can lead to correct predictions. But one must always remember that this is a way of understanding imposed on mathematical reality, not necessarily a description of what is literally occurring at the quantum level. This distinction is subtle but important. It reflects a deeper truth about quantum mechanics, that the theory describes probabilities and correlations, not necessarily the detailed mechanics of individual events. We cannot peer into the quantum vacuum and observe the virtual particles with our eyes, even with the most powerful microscopes. We can only observe the effects they produce. The Casimir effect is one such effect, a window into the hidden activity that persists within the supposedly empty void. And yet, the fact that we can measure and predict these effects based on quantum field theory provides strong evidence that the theory is capturing something real about the world. The vacuum has energy. The fields permeating space are genuinely active. The void is not truly void. These conclusions follow not from speculation, but from the careful measurement of forces between metal plates, separated by distances so small that they exist at the boundary between the visible and invisible worlds. The Casimir effect, while subtle and beautiful in its own right, points toward something far larger and more mysterious about the cosmos itself. The energy density of the quantum vacuum is not merely a laboratory curiosity. It plays a role in some of the deepest mysteries that occupy modern cosmology, mysteries that have gathered urgency and significance in the decades since the Casimir effect was confirmed. In the 1990s, roughly 50 years after Casimir made his prediction, astronomers observing distant supernovae made a startling discovery. The universe, it seemed, was not merely expanding as had been understood since the early 20th century. Rather, the expansion was accelerating. The universe was speeding up as if some vast repulsive force were pushing all things apart. This was unexpected, counterintuitive, and profound. The most natural explanation was the presence of a form of energy that pervaded all of space, an energy that did not clump together with matter but remained distributed uniformly throughout the cosmos. This energy became known as dark energy. The question naturally arose whether this dark energy might be related to the vacuum energy predicted by quantum mechanics, the zero-point energy associated with quantum field fluctuations that Casimir had cleverly revealed. In principle, these two concepts seemed connected, linked by the deep mathematics of quantum theory. The vacuum energy density calculated from quantum field theory was a natural candidate for explaining both the Casimir effect and the universe's accelerating expansion. Yet here a puzzle emerged, a puzzle that remains unsolved and deeply troubling to physicists even today. The vacuum energy calculated from quantum field theory, the energy in the quantum fluctuations of all known fields, is far larger than the energy density of dark energy inferred from cosmological observations. It is larger by an almost incomprehensible margin, a discrepancy of such staggering proportions that it seems impossible to dismiss as a mere computational error. This became known as the cosmological constant problem, a mystery that sits at the intersection of the infinitesimal and the infinite, connecting the quantum vacuum to the structure of the entire universe. The resolution to this puzzle remains unknown, waiting somewhere in the future of physics. Perhaps our understanding of quantum field theory requires modification at cosmological scales. Perhaps new physics beyond our current theoretical framework plays a role. Perhaps the vacuum energy and dark energy are not directly related after all. The Casimir effect confirmed that quantum vacuum fluctuations are real, that they manifest in measurable ways, and yet the full implications of this reality for understanding the cosmos remain tantalizingly out of reach, waiting for some future generation of physicists to illuminate. While the Casimir effect remains one of the most delicate and esoteric phenomena in physics, its implications continue to unfold. In the realm of nanotechnology, and in the design of increasingly miniaturized devices, the Casimir force becomes significant. As electronic components and mechanical devices are shrunk to smaller and smaller scales, the quantum vacuum exerts forces that can no longer be ignored. Engineers designing nanoscale machinery must account for the attractive force between surfaces separated by nanometer distances, distances so small that the quantum effects become dominant. In this way, the quantum vacuum becomes an engineering concern, a practical consideration in the design of the future. Some researchers have contemplated whether the Casimir effect might be harnessed to produce new technologies or to generate useful work from the quantum vacuum itself. These ideas remain highly speculative and perhaps constrained by fundamental thermodynamic principles. Yet the theoretical exploration of such possibilities continues to engage the minds of physicists and engineers, who are drawn to understanding the full implications of what the quantum vacuum might offer. More immediately and realistically, a deeper understanding of the Casimir effect will be important for the continued miniaturization of electronics and the design of future nanoscale devices and systems. Beyond these practical considerations lies a deeper significance that touches the very heart of our inquiry. The Casimir effect stands as a profound reminder that our universe is far stranger and more complex than our everyday experience would ever suggest. Empty space is not empty. Nothingness is not truly nothing. The gulf between our intuitive understanding of reality and what quantum mechanics reveals through careful measurement continues to be vast and humbling. As we continue to probe the nature of the quantum vacuum, new surprises may yet emerge from the depths of seemingly empty space. Future experiments with improved precision and sensitivity will continue to test and refine our understanding. New tools and techniques will gradually illuminate the nature of vacuum fluctuations and their role in the larger cosmos. The relationship between the energy of empty space and dark energy will likely remain an area of active investigation for many years to come. The quantum vacuum, far from being a solved problem, remains one of the most profound and mysterious aspects of reality that physicists and philosophers continue to contemplate. And so we return in this final chapter to the question with which we began: what is nothing? We have journeyed through the mathematics of quantum fields, through the laboratories where delicate measurements confirm the reality of the invisible, through the connection between the infinitesimal vacuum and the cosmos itself. The answer that emerges is far stranger and more beautiful than any simple response could capture. Nothing, as it turns out, is not nothing at all. The void seethes with activity. Emptiness overflows with presence. The space between atoms is not a blank canvas, but rather a dynamic, fluctuating medium, a sea of probability, a realm of perpetual motion, a manifestation of fields that extend throughout the entire universe. Casimir showed us, through mathematics and prediction and careful measurement, that this invisible activity leaves traces. It exerts forces. It shapes the behavior of the material world. What was theoretical became observable. What was invisible became measurable. There is a deep resonance in this discovery that extends beyond its technical significance. For millennia, human cultures have contemplated emptiness, nothingness, and the void. Philosophers have meditated on the paradox of nothingness. Mystics and poets have long sensed that beneath apparent emptiness lies infinite potential. Modern physics, arriving at these insights through a completely different path, through mathematics, measurement, and experimentation, provides a kind of confirmation that the deepest intuitions of contemplative traditions were not entirely misguided. The quantum vacuum does not contradict these older insights so much as deepen them. It provides a physical mechanism, a mathematical framework, and empirical confirmation for the paradoxical truth that emptiness is full, that nothing contains everything, that the void is pregnant with possibility. Casimir's prediction and its experimental confirmation represent a moment when abstract theory touched the deepest reality of existence and found it more mysterious and more wonderful than anyone had imagined. And as we contemplate these truths, settling more deeply into stillness, there is a comfort in this knowledge. We are surrounded by forces we cannot see, immersed in fields that extend beyond our perception, part of a universe far more subtle and complex than our everyday experience reveals. There is a peace in this understanding, a sense of belonging to something vast and profound. The quantum vacuum, empty yet full, silent yet active, invisible yet influential, continues its eternal dance beneath the surface of all things, with or without our understanding or observation. Let yourself drift now into the quietness of these mysteries. Picture, if you will, a laboratory late at night, illuminated only by the soft glow of instruments and the distant light of stars beyond the windows. The two metal plates sit in their vacuum chamber, separated by distances so small that no unaided eye could perceive them, and yet through them flows a presence, a subtle force revealing the activity of empty space itself. In the darkness between those plates, fluctuations occur. Waves in fields, patterns emerging and dissolving, energy moving in ways we can only describe through mathematics. And yet these invisible fluctuations are not separate from you. They are not distant or foreign. They occur in the space between the atoms of your body, in the void that surrounds you in every corner of existence. The same quantum fields that produce the Casimir effect between metal plates in a distant laboratory permeate your being at this very moment. You are, in a very real sense, made of quantum vacuum fluctuations, organized into patterns of such complexity and beauty that they give rise to consciousness itself. So allow yourself to rest now in this knowledge, sinking more deeply with each breath into peaceful acceptance. The universe is not the cold, dead mechanism that an earlier age imagined. It is alive with subtlety, rich with hidden activity, fundamentally mysterious in ways that mathematics can approximate but never fully capture. The Casimir effect is merely one small window into this deeper reality, yet through it we glimpse something of the profound strangeness and wonder that underlies all existence. Let the rhythm of these ideas carry you gently into quieter and quieter places, as if you were drifting on a sea of quantum possibilities, resting in the embrace of a universe far stranger and more beautiful than we could have imagined. In the darkness, in the emptiness, in the supposed nothingness between the stars and between the atoms of your body, something eternal and infinite continues its patient work, creating and sustaining all that is. And so you drift deeper and deeper now into the peaceful darkness, carrying with you the knowledge that emptiness is full, that nothing is everything, that the quantum vacuum sings beneath the surface of all things with a song so subtle that only the most delicate measurements can hear it, yet so real, so profound, so true. The laboratory fades. The metal plates dissolve into memory. And you sink gently, gently into the infinite stillness that has always been waiting for you, the darkness that holds all light, the silence that contains all sound. End of script. Total word count, 5,847 words.